Okay, so in this video, I want to talk about uh, something related to the Grassmannian, which is the tangent bundle of the Grassmannian. So so let me start by recalling some basics. Uh, so first of all, what is a tangent bundle? So a tangent bundle on a manifold M. So suppose you have some manifold M, and then you have a particular point X on that manifold, and on that point you have a well-defined tangent space. So So you can take some basic examples to visualize this thing. For example, if you have a circle, then you can see that at each point you have this tangent, and then so at a certain point you have this tangent space, which is a one-dimensional vector space, and then you can vary the point. So on each point you have this tangent space. So as the point varies, the tangent space also varies. And if you look at the collection of all these tangent spaces, so that gives you the tangent bundle. So uh, yeah, so for example, you can also take the sphere. So this is the two sphere embedded in R3, and then at each point you can look at the tangent plane. So visually that is your tangent space or tangent plane at that point. And as the point varies, you take uh, the disjoint union of all those tangent spaces. So that is your tangent bundle. So yeah. So yeah. So M is a manifold, and suppose I take a point X in that manifold, then you have this tangent space at the point X for all X in M. And then what is your tangent bundle? That is the disjoint union of these tangent spaces as X varies over M. So uh, so you can show that this is a smooth manifold. That is to say that if M is a manifold, if you start with a manifold, let's say smooth manifold, and then at each point you look at the tangent space, you take the disjoint union of all of them as X varies over M. That is your set Tm. That is a set till now, and then you can equip this Tm with the structure of a smooth manifold. First of all, you can show that this is a manifold, and then it's a topological manifold, and then you can put a smooth structure on that. So by putting a smooth structure, what we mean? I mean, locally you have to give charts. So locally, for each neighborhood of each point, uh, you have to give coordinates in Rn. So that is what is meant by giving a smooth structure. So this tangent bundle is a smooth manifold. So now uh, we are interested tangent bundle of the Grassmannian tangent bundle of the Grassmannian, so which I defined in the last video, last two videos. This is denoted by, so yeah, Grassmannian, let's say GRKV. Suppose you have some n-dimensional vector space uh, over the real, and then if you look at the Grassmannian of degree k, that is a smooth manifold, as I explained in the last video. This can be realized as uh, the quotient of GLV by some closed subgroup. So yeah, so there is a homogeneous space, that is the group GLV acts on this space transitively. So this can be realized as GLV modulo the stabilizer of some particular point, which is a closed subgroup of GLV, and it is also a smooth manifold. Now we are interested in the tangent bundle of this thing, the space grasp, this GRKV. Okay, so before that, let me just talk about this. So there is this particular type of uh, vector bundle on the space GRKV. So what is vector bundle? So similar to the concept of the tangent bundle, where on each point you have a tangent space. In general, on each point you can attach a vector space. Suppose you have some manifold M, and on each point you can attach some vector space, and you can do it in a smooth way. So roughly that is what a vector bundle is. So tangent bundle is a special case of the vector bundle, where at each point your vector space is precisely the tangent space. So on GRKV there is this tautological bundle. Tautological bundle. So what is that bundle? This is a vector bundle, and how do you define this? Suppose this is your space GRKV. So look at a particular point X. That means this. So what is this X? This X is a particular k-dimensional subspace of your vector space V. That is what a point in the Grassmannian is. So that point corresponds to some subspace of the vector space V. So on X, we attach that vector space itself. So that is your uh, tautological bundle. And as you can see that this is defined kind of tautologically. So the point defines, each point defines a particular subspace, and you are attaching that subspace on each point. That's why it is known as the tautological bundle. So at each point, this is just a subspace of your k-dimensional subspace of your vector space V. This is a tautological bundle. And then there is also this trivial bundle on um, on any manifold M. So what is that? That is just M cross Rn. So you have M, and then at each point you can attach an n-dimensional vector space Rn, and you can glue them together globally in a smooth way. So that is your M cross Rn. So yeah, so this M cross Rn is a trivial bundle. So equipped with the natural projection map x comma v goes to v goes to x. So at each point is at each point x you can attach the vector space Rn, and globally you can glue them in a smooth way. So that is your trivial bundle on a manifold M. Now we're interested in the tangent bundle of uh, tangent bundle of this GRKV. Yeah, so how to do this? So in the last two videos also, uh, you have observed that, so you should always think of this Grassmannian as quotient of the Lie group GLV. So GLV acts transitively on that space. So I will just use that action, the GLV action, that orbit map, to conceptualize this whole thing. So what is the orbit map? So this is your GLV, and this is your uh, GRKV. And then suppose you fix a particular subspace W. You fix a particular subspace W, a k-dimensional subspace W. So you have this orbit map. So suppose you have a invertible linear transformation A, and that goes to AW. And you know that this action is transitive. So uh, this W, if W is k-dimensional, then AW will be another k-dimensional subspace. And since this action is transitive, so this will be a surjective one. So in fact, phi is smooth. So this is just an easy observation. This is more or less how GRKV is defined. I mean, GRKV is a homogeneous space for the Lie group GLV, and GLV naturally acts smooth. So this phi is smooth. So you can differentiate. You can differentiate this map at the point uh, identity. So where does identity go? Identity go to W only, isn't it? The point identity goes to W. because I dot w is just w. I is the identity linear operator on V. So I can differentiate the map d phi at the point identity. So take the differential of phi. This is a smooth map, so I can take the differential of phi at the point identity. So this is a map from tangent space at the identity of GLV to tangent space at the point W of the space GRKV, right? So that is how the differential works. If you have a smooth map, then at each point you can differentiate to get the derivative map between two tangent spaces. But but what is this Ti of GLV? This Ti of GLV, that is nothing but end V. This is a basic exercise that you should do on your own. So in the Lie group terminology, the Lie algebra of the Lie group GLV is just end V. So this is just endomorphism of V. So that is same as hom VV. So you have a map from hom VV to uh, okay, let me just go back there. Uh, so this was our derivative map. This is just uh, end V. End V is nothing but hom VV. So we have a map from hom VV to tangent space at the point W of the space GRK. So there is a map from hom VV to TW of GRKB, and then uh, yeah. So, but the point is that this is not this is not an isomorphic. I mean, the map uh, d phi, this map d phi, this is not an isomorphism because the space GLV and the space GRKV, they have different dimension. Their dimension as a manifold are not same. So this d phi is not an isomorphism. It's not an isomorphism. Not an isomorphism. So now you can do one thing. So since W is a subspace of V, so there is this canonical inclusion of W inside V. And suppose I take a particular element, I pick a particular element from hom VV. This is a linear transformation from V to V. So this is a linear transformation from V to V. And then from V to V mod W, you have this natural quotient map. So Q is quotient map. Because W is a subspace, so from V to V mod W, you have a natural quotient map or projection map. So given any F in hom VV, you have a map from W to V mod W. So, so let us put it in a diagram that from hom VV to TWGRKV, you have a map, and from hom VV, you have a map into hom W V mod W. Just by this procedure, the procedure that I have defined. Include W inside V. From V to V, you have some map F, and from V, you have a projection to V mod W. So compose all these maps. You get a map from W to V mod W. So so given any map in hom VV, I get a map in hom W comma V mod W. And this will induce a map between these two. So suppose this map, so this map was D phi, and suppose this map, let's call it alpha. So then there exists a unique mu, such that what will happen, such that your d phi is equal to mu followed by alpha. And you can actually check that this map is an isomorphism, because it is almost the way it is defined, because your map d phi takes hom VV to TW at GRKV, and then you have this map from hom VV to hom W comma V mod W. That is by this procedure, and that will induce an isomorphism from hom W comma V mod W to TW GRK. So you can check the details. I mean, take it as an exercise. So this is doing things point wise. So at each point X, the tangent space is isomorphic to hom WX comma Vx modulo Wx. I'm putting x in the subscript to denote that Wx is the vector space attached to the point x. Now, if you do this for every point, you get the whole tangent bundle. That is your tautological bundle W. And at each point x, if you attach the vector space V, you get the trivial bundle. So yeah, so on the bundle level also, so this uh, goes through at the level of bundles. So you can write that tangent bundle of GR KV is nothing but the Hom space between two bundles W comma V mod W. So initially, just do not get confused with the notation, because initially I was doing it point wise. So now I'm writing it on the bundle level. So here by W I mean the whole bundle, whole tautological bundle W. But previously I was writing W to denote a particular point. And your tautological bundle is precisely at each point X you attach the vector space W itself corresponding to that point. So yeah, so that is the thing. And maybe I will finish the video by talking about some general philosophies. So these homogeneous spaces are very important throughout the whole mathematics. Homogeneous spaces are important. That is the upshot in general. So these Grassmannians are a particular example of the homogeneous space. So Grassmannians are just quotient of the Lie group GLV by some closed subgroup. Similarly, there are other homogeneous spaces. For example, suppose you take the GLV itself. Take the GLV itself. These are Lie group. And then suppose I take the so let's call it G. G is equal to GLV. It's a Lie group. And suppose I take the Borel subgroup to be B. So on the matrix form, this is just a set of all upper triangular matrices. Set of all upper triangular matrices. This is a Borel subgroup. So then you can look at the space uh, G mod B. So this is also a homogeneous space for G. So G acts transitively on this space G mod B. And then, I mean, there are interesting line bundles on this space. So, over G mod B, you have some interesting bundle. I'm not explaining what is this. This is some particular line bundle. So I'm just giving some reference kind of thing that you can look these things in detail. I mean, these are very important. So you can learn it on your own. So take the Lie group GLV, take the closed subgroup of upper triangular matrices, that's your Borel subgroup. So then G mod B, this is a homogeneous space for G, and then there is some special kind of line bundle L. So line bundle is a vector bundle where at each point the vector space is one dimensional. That is a line bundle. And then there is something called cohomology of that line bundle. So this is the ith cohomology of G mod B with coefficients in L lambda. That is a line bundle. So on this homogeneous space, we have a line bundle L lambda, and you can calculate the cohomology of that line bundle. And this is related to the geometric side of the representation theory of G. So this cohomology space carries in G action, carries in G action. So it captures the representations of G. So I mean, in general, you have to. So yeah, so maybe you start with some compactly with G, and then complexify that Lie group. So let me write that in a Lie page. Think I'm running out of pages. Yeah, so yeah, let me just create a new whiteboard. So I'm just trying to give some examples of the following thing, that on homogeneous space there are some interesting vector bundles, and that can be studied from various point of view. And one of them is study the shift cohomology. The cohomology that I'm talking about here is the shift cohomology. So look at the shift cohomology of those vector bundles, and those are in general important objects in mathematics. So this line bundle on the not the line bundle, not the tautological bundle, uh, is a natural bundle on the Grassmannian. And that has also some applications. Maybe I have to think about it. Right now I cannot remember anything, but okay. The thing that I wanted to talk about is that suppose you take a compact Lie group G. Yeah, so yeah, let's say compact connected. Takes a compact connected Lie group G, and then GC is the complexification of G. So maybe if you do not understand these terms, just keep in mind the example that G is your unitary group. UN, and your GC is just GLN C. This example you can always keep in mind. And in particular, we are mostly talking about GLNC throughout these videos. So then inside this GC you have the Bore subgroup B. So then you have this homogeneous space G complexification mod B, and then you have some interesting line bundle. Then you can look at the Schiff cohomology of that. So that captures all representations of compact group G. So yeah, so this is the general philosophy of Bore-Weil-Bott. So you can look it up on your own. So this is a particular example that I'm talking about. A particular example of the fact that on these homogeneous spaces there are nice vector bundles naturally constructed using uh, some character of the Bore subgroup. So in the previous case, there was a natural vector bundle which is a tautological bundle on the Grassmannian. You can also study the cohomology of that vector bundle. I think that is also something interesting. But anyways, the thing that I'm talking about, the Bore-Weil-Bott theorem, that is essentially that this thing that if you look at the ith shift cohomology of GC mod B over the line bundle A lambda, that captures all the representations of the compact group. So yeah, whenever you have some group action on some homology space, so you can expect that homology space will capture all the representations of your group. So that is a main philosophy. So yeah, the upshot is that studying vector bundles are important. So when you study topological spaces, uh, if you're a topologist, you want to understand the topological spaces. If you're a geometer, you want to understand differentiable manifolds and so on. And there are many things. Initially, you learn many things to distinguish topological spaces. There are tools like homology, cohomology, and so on. And yeah, I mean, you have homotopy groups and other things, the concept of homeomorphism and so on. And then there is also this concept of vector bundles. How many vector bundles, in how many ways you can put vector bundle structure on a manifold that reflects the structure of the manifold itself. That's why vector bundles are important. I mean, in mathematics, this is the general philosophy. You always try to put some extra decoration on the already given fundamental object. And what kind of extra decoration you can put on that object that captures the geometry of the object itself. So vector bundle is one special case of that thing, that general philosophy. Yeah, so I will stop.